introduce the first speaker of this afternoon, Manuel Rivera from the University of Miami and Cinvestav. He's going to talk about string topology, coproduct, geometric and algebraic aspects of chain diverse. Thank you.
Thank you for the invitation. It has been a lovely conference and a lovely city. So I will be talking about a coproduct on the homology of the free loop space of a manifold, which is part of a family of operations known as string topology. So I will start by introducing a little bit of the history of string topology, the constructions that gave birth to this field. Then I will talk about this coproduct, which is a 1-to-2 operation in the homology of the free loop space of a manifold, which is, presents some very interesting and subtle transversality constructions at the chain level. Then I will proceed by making some remarks of certain constructions in Hochschild complexes of Frobenius algebras, which are intimately related to this coproduct. Okay, and I will describe how these two theories are related. On one side, we have a purely algebraic theory of Hochschild complexes. On the other side, we have a geometric theory on chains on the free loop space of a manifold. Okay, so if you don't follow the first part, you can still follow the second part without any problems. So, good. How do I get rid of that little thing? Disappears.
In a moment.
Okay, there you go. Thank you. So string topology. String topology is about intersection type constructions on chains or families of loops or paths on a smooth closed manifold. And it began with Chas and Sullivan's remarkable observation of the fact that even if we don't have Poincare duality for the free loop space of a manifold, there is still an intersection product lifting the intersection product in the underlying manifold. Okay? And the construction of this product, called the loop product, is as follows. So let's say we have two chains, U and V, on the free loop space. So by chains, I mean geometric chains. So I'm thinking U and V are manifolds with corners, and alpha and beta are smooth maps. What do I mean by smooth? I mean that the adjoint maps are smooth. So the map from U cross I to M is smooth, and also the map from V cross I to the free loop space is smooth. So given two chains on the free loop space, I can consider this evaluation map just by evaluating at the base points of each chain. And I want to intersect transversally this evaluation map alpha corresponding to alpha cross beta with the diagonal. Okay. So the idea is that you have these two chains on the free loop space. You look at the chains in M obtained by projecting at the base point, and you want to deform the chains on the free loop space such that these projections are intersect transversally in the underlying manifold. Okay? So assuming this transversality, we have that the inverse image of the diagonal will be a nice geometric object, in this case a manifold with corners of dimension I plus j minus k, where k is the dimension of the manifold. Okay? And now I can define a new map over this inverse image by concatenating the corresponding loops whose base points agree on the point xy in this case. So a point xy in this inverse image has a property that alpha x at 0 equals alpha at b of y at 0. So I can concatenate those loops. Okay? So this defines a product on on the free loop space modulo this transversality assumption. Okay, and that's the idea of the construction for the loop product and intersection type products on the chains of the free loop space, lifting the intersection product on a closed manifold of dimension k. Okay, so that was the first construction of a string topology operation. And this construction is well defined in homology. The transversal intersections can be justified at the level of homology, and it is a graded associative and commutative product of degree minus k, which means that lowest degree by k, and it is part of a much richer algebraic structure, which a structure which was actually known by physicists, not in this context, but in a different context. So the loop product is compatible with the rotation operator B. So in the free loop space, we have an action of the circle given by rotation of loops, and this action gives rise to a map of degree +1, right? You have a chain, you can consider the one parameter family of chains given by rotating the loops, and the loop product is compatible with this operator B in giving rise to a structure known as a BV-algebra. Okay, and this BV-algebra is defined as follows. The structure of a BV-algebra is the following. First, the homology of the free loop space with respect to the product is a graded associative and commutative algebra of degree minus k. B squares to 0, and the operation defined as the failure of B being a derivation of the product is a derivation of the product itself. Okay. So B is not a derivation of the loop product, but the failure defines a 1 to 2 operation that is a derivation in both variables. So it is satisfying the Poisson identity with respect to the product. Okay? And in particular, one can show that this bracket operation is satisfies Jacobi identity and is anti-symmetric, rated symmetric. Okay? So this is a BV-algebra structure. Okay. And this bracket is also known as the loop bracket. And let me say that it can also, it also arises from a chain homotopy for the commutativity of the loop product at the chain level. So the loop product at the chain level is not commutative, but it's commutative up to homotopy. You can look at this chain homotopy, you can symmetrize it, and you get a bracket operation, and in homology, it agrees with this operation defined as the failure of B in satisfying lightness with respect to the loop product. Okay, so there's a lot of structure in the free loop space with respect to this intersection type operation. Okay. Now, I want to talk about another operation which is, I think, much more subtle and mysterious in some sense, known as the loop coproduct. And it was also described by Sullivan and by Mark Goresky and Nancy Hingston in a different setting using the Morse theory for the free loop space. And the idea is that it considers a single chain of loops and all self-intersections in that single chain and splits the loops at intersection points. Okay? So let me describe this construction in the same way I was describing the loop product. So we start with a single chain in the free loop space. So I'm thinking of U again as a manifold with corners of dimension I. And I consider the following evaluation map. From U cross the interval, I have a point in U and a parameter t. and I evaluate my loop alpha x both at 0 and at t, at that parameter, okay? And I want to intersect this map with the diagonal, okay? So I'm going to take this inverse image. Let's right now assume, I haven't said anything about the manifold structure here. Let's just consider this set theoretically for a second. So over this inverse image, I can split loops at these self-intersections, right? What is a point in this inverse image is given by x and t, such that alpha x at 0 equals alpha x at t. Okay, so the loop at x has a self-intersection, and then I can split this loop by running the loop alpha x from 0 to t. I get the first factor, and then by running the loop alpha x from t to 1, I get the second factor. Okay? However, there are certain subtleties that we have to take into account here. The first one is that this evaluation map, E of alpha, will never be transverse at the boundary of the interval. Okay? In fact, this inverse image here always contains a copy of u cross 0 and u cross 1, no matter what deformations I make. Okay? Because x and 0, E of alpha of x0 will always lie in the diagonal. Similarly for x1, E of alpha of x1 will always lie in the diagonal. Okay? So the idea here is to achieve transversality for this circle E of alpha, the restriction of E of alpha to the open part of the interval, in a particular way so that the closure of this inverse image, once we achieve transversality for the inverse part, is a manifold with corners. Okay? So we have to achieve this transversality controlling the closure of the inverse image of the open part. Okay? Another issue that we have to take into account is that I have crossed U with something that has boundary. So I've created new boundary, right? When I take this closure, I create a new boundary coming from the boundary of the interval. So in particular, this construction will not define a chain map. It will not commute with the boundary operator on chains because I have crossed with this interval that has boundary, right? So, and I eventually want to get an operation in homology, right? So how to deal with this? Well, we observe that for all points x in the inverse image, all points x0 and x1 in this inverse image, each of these maps has a factor in Lm which will be a constant loop, right? Because for example, for x0, the first loop will run alpha x from 0 to 0. And then it will run alpha x from 0 to 1, right? Will it come back? There you go. Okay, so in fact, we can kill this new boundary that I have created by working modulo constant loops, okay, with the relative pair Lm and M, where I'm thinking of M inside the free loop space as constant loops, okay? Or there's also a way of modifying the construction of V algebraically by subtracting some terms so that we can work in absolute homology without having to mod out by constant loops. But you always need a modification in order for this operation to pass to homology. Okay, good. So we have a similar structure to the one we saw for the loop product. Namely, this coproduct V passes to the relative homology of Lm modulo constant loop, and together with B, which is also well defined in this relative homology because it preserves the constant loops, right? It defines a BV coalgebra of degree 1 minus k. So remember that this new operation V is of degree 1 minus k, right? You take a chain of degree I, you cross it with this new parameter, this new interval, and then you take the inverse image of the diagonal, which is of degree k. Okay, so the dimension of U is I plus 1 minus k. So the coproduct is of degree k, and it's compatible with the rotation operator in a BV coalgebra. So what's a BV coalgebra? It's exactly the dual of a BV-algebra, right? So the homology, the relative homology, together with the coproduct is co-associative and co-commutative. B squared equals 0. And the 1 to 2 operation, which measures the failure of B on being a co-derivation of B, is a co-derivation itself. So you just take the diagram defining a BV algebra and reverse the arrows. Okay? And in fact, in particular, you can prove that by an algebraic argument that this delta is actually a Lie co-bracket of degree 2 minus k. Okay, and this is called the loop co-bracket. So this coproduct V and the loop product also induce operations in equivariant homology. Okay, with respect to the action of S1 in the free loop space. And in fact, the loop product induces a bracket in equivariant homology, and the loop coproduct induces a co-bracket in equivariant homology, both of degree 2 minus k, and they are compatible in the equivariant homology of the free loop space, giving rise to an involutive Lie algebra. Okay, I will not define this algebraic structure because I will not get into it, but I will say that it's related to, for example, symplectic field theory through the connection of the equivariant homology of the free loop space and linearized contact homology of the unit cotangent bundle of the map. Okay. So we would like to understand these constructions at the chain level for several reasons, in particular for applications to symplectic topology. And in order to do this, we have to keep track of the deformations we made to achieve transversality, or work in a context in which the chains are already in general position. Okay, and we can take intersections without worrying. Okay, and then we have to prove that this context, by context I mean the chain complex, is quasi-isomorphic to the original one. It computes the right homology. Okay? So I will actually give examples of both philosophies in some sense. Okay? Let me start with the geometric constructions, in which I'm actually keeping track of these deformations explicitly. So the setting we use in order to achieve this transversal intersections is the round chains with corners. So let me explain what I mean by these. So first, they were introduced by Fukaya and his student Iri in order to study structures around the loop product. Okay, and they used the round chains without corners, but in order to study the coproduct, we found out that we have to take care of corners. Okay, so what are the round chains? So modulo some technicalities, the vector space of the round K chains is the vector space over R generated by pairs where phi is a map from a manifold with corners U to the free loop space, a smooth map. And eta is a compactly supported form in U, okay? And the dimension of this chain, K, is n minus m, where n is the dimension of the manifold, and m is the degree of the differential form. Okay, so how to think about, there's some relations. So we impose linearity on the form part, and we declare two pairs to be equal if there is a surjective submersion pi intertwining two pairs in this way. So pi intertwines the map parts, and the form parts are related by integration along the fiber with respect to pi. Okay. And now there is a differential on these Durand chains given by the alternating sum of the geometric boundary of your manifold with corners and restricting your form to the boundary of your domain, pulling back to the boundary, and then taking the exterior derivative of the form. So how to think about this pair? Well, I think of it as the cap product of a geometric chain and a differential form. Okay? So what's the idea? The idea is that I have a map in the free loop space, and I want to have certain transversality conditions that might not hold a priori, right? So I can take this map and I can thicken the domain to a bundle. Let's say you consider a bundle over U, and you deform the map phi as you move along the fibers on this bundle over U to achieve the transversality you want. Okay, to do the string topology operations. So, but however, I've created new space by taking this bundle. So I've changed the dimension of the geometric chain. Oh, so I wedge with the Thom form of this bundle, the form part, to kill those new directions. Okay, so it's a very useful way to do transversality in a geometric context. And I forgot to mention here, but one can prove that this new complex that I defined computes the singular homology of the free loop space. Okay? Yeah.
Why are you using forms rather than singular cochains or something?
You could use singular cochains. Let me think. You could use singular cochains, yes. You could use singular cochains. In fact, Sullivan proposed a version of these Durand chains using singular cochains in one of his chain level string topology papers. So you could use. I'm thinking maybe we might run into some problem. I'm not sure right now, but yeah, you could use singular cochains. Okay, and Erie uses this framework to lift the loop product to the chain level. Okay, so what he does is that he describes a chain complex quasi-isomorphic to these Durand chains, such that the transversality is always satisfied. And the quasi-isomorphism is given by this thickening process that I described. Okay? And in this new complex, he can define the loop product without any problems. And he can even lift the BV-algebra to the chain level. That means giving an action of a DG operand weakly equivalent to chains on the frame little disc operand. Okay, so it's like the link type conjecture at the chain level. he's solving.
They could have all sorts of dimensions, like in the Kuranishi structure.
Yes, it's exactly very similar to this. Yeah. Okay, so let me describe the chain level construction for the coproduct now, using these Durand chains. Okay, and this is joint work with Dingu Yang. Okay, so we have a Durand chain given by phi and omega, and recall we have this evaluation map into M cross M by evaluating in 0 and t, and we have the open evaluation map, the restriction of the evaluation map to the open interval. So the idea again is to replace alpha by a thickened chain, right? Such that the closure of the inverse image I was looking at is a manifold with corners. Okay. So I want to control the closure. So how do we achieve this? So this is the thickening here. So E is a Whitney sum of these two bundles over U. So delta is the injectivity radius of a chosen Riemannian metric on M. Phi dot 0 is a map from U to M. So I pull back to U these bundles, and now I deform my map. I deform my map phi using along the new bundle E using this new map theta by using the exponential map with respect to the Riemannian metric and doing the following. V and W are vectors in the fibers. I apply a parallel transport along the loop G, phi of x composed with G, where G is just a reparametrization of the loop that will help with smoothness. So it's a technicality. You don't have to worry too much about that. But the point is that these p's, they bring your vectors V and W to the domain of this exponential map. And then I use some smooth functions, lambda 1 and lambda 2, to control the closure of the inverse image of the manifold, of the diagonal. Okay? So these smooth functions are the ones that will let me control as I approach to t equals 0 in a nice way. Okay? So I won't go into the details here, but the point is that with this new thickening, your evaluation map, your open evaluation map is now transversed to the diagonal. And moreover, for t close to 0, the self-intersection equation can be described as a graph of a function which extends smoothly to t equals 0. So that means that at t equals 0, I can provide coordinates for the manifold with corners using the graph of a function, solving for a variable. So, and this gives a manifold structure, a manifold with corner structure in the closure of the inverse image that I'm looking at. So the idea is to use these functions, deform very carefully your map along this bundle in a way that I achieve the desired transversality. Okay? Yeah?
Sorry, what does your construction give in the classical case when it's just a surface? And you have Toraev's co-bracket kind of in the usual. So how do you lift it? So just two-dimensional real case.
Yeah, so in this case you're actually looking at the H0, the H0 homology. So but it's a
put it back on the previous one.
Sorry?
So could you put the previous slide?
Yep.
So which choices do you make there? So what happens?
So
if your M is just
Is it related to the
two-dimensional.
Goldman bracket or anything like that?
yeah, but for,
It's Toraev's co-bracket.
The co-bracket,
and
yeah.
Goldman's bracket, right? So
but
what happens there?
it's slightly different here because we don't have this operation at the level of a surface. Because Toraev's co-bracket is actually an equivariant operation. Okay? So this operation is not really defined on the surface, this coproduct operation, because of degree reasons. It's of degree 1 minus k. The co-bracket is of degree 2 minus k. So in fact, the co-bracket of Turaev is defined on the H0 homology, equivariant homology of the free loop space on the surface, namely on the homotopy classes of loops without a base point. Here I have a base point.
Okay,
So-
with the base point. But however, I just want to understand it in this case. So.
But again, this operation is not defined on surfaces because of degree reasons. So you cannot make sense of this co-bracket for curves, for base curves in surfaces. Okay, you need to saturate by the S1 action. I can explain later this point. Okay, but yeah, you cannot visualize this operation in terms of curves in the surface. Is the point. So finally, as I said, you do the intersection you want to get this manifold with corners, and now you split at the intersection part, and you kill your new directions by using a Tom form U on this new bundle E. Okay? And now the theorem that we proved is that we have constructed a family of operations given rise to a co-A infinity algebra on these Durand chains, whose first operation is the differential, and second operation is this coproduct that I have described here. And for example, mu3 is the chain homotopy for the co-associativity of the coproduct mu2. And we have coherent maps. So we have to take care of many issues like this, like taking closures of inverse images and controlling these closures in order to have a geometric theory. Okay, and there's a similar construction for the co-bracket. Okay, for the loop co-bracket, giving rise to a co-L infinity algebra at the level of the Ram chains. Okay, and we're in progress of lifting the BV coalgebra structure to the chain level, and moreover, we want to give chain level lift of the Levi algebra to an equivariant version of the free loop space, of the chains on the free loop space. Okay, so
You already over the time.
okay, so I think I will not have time to discuss about the algebraic theory, but let me say something a little bit. So you can, the Hochschild, I'm going to pass that. You can define the Hochschild chain complex of a differential graded algebra. And Jones and Chen proved that in the simply connected case, this computes the cohomology of the free loop space. Okay? So you can do similar string topology constructions at the level of Hochschild complexes. Okay? And you can, to do that, you have to choose a Frobenius model for the differential forms on your manifold. That means lift Poincare duality strictly to an algebra, a differential graded algebra, which is quasi-isomorphic to the differential forms. And once you have that strict Poincare duality, you can do similar algebraic constructions like string topology operations, but using the strict Poincare duality, it's easier to do these intersection type operations because you have the philosophy in mind that all your intersections can now be taken freely. So this is an algebraic theory which follows the second philosophy that I said, that you have a context in which you don't have to worry about transversality because you solve this first. And we can recover the coproduct, the loop product, and give new describe compatibilities between these two, and we actually give new interpretations of these two at the chain level, which I wanted to tell you, but I don't have enough time. So thank you for listening.
We don't have time to questions right here, or please ask him at the coffee. We have 10 minutes for the next talk.
La homología. Pero no sé, esto como que no sé qué, tengo que preguntar a ¿Has pensado en este coproducto para Hochschild? Hay que describir, no sé.
Pero sí,
Ya.
pero no, pero en este es un estándar, pero esta parte no es.